If x is 0, this gives me t squared minus t cubed equals 0. Right. And so t squared equals t cubed. And t is not going to be 0 because 0 gives us the origin. So if it's not 0, I'm allowed to divide by it. But probably better to divide by t squared. And I get 1 equals t. So the t value up here is 1. And when you're given a problem in this form, where you're told your endpoints in terms of pairs of numbers, in terms of x and y, and if you're going to use parameters to do the job, then you've got to figure out the parameter values to go with that. A lot of the problems in the book, they just say, okay, here's the parameterization, r of t equals something t times I and something t times j, and you're going to find the arc length between t equals 5 and t equals 12, or whatever. That kind of goes against the grain for me. What we're used to in our algebra and calculus and all that is knowing the points in the plane. You know, what are the x and y coordinates? And any other quantities, well, we need to calculate. So I do sometimes give you that kind of situation where I tell you the t values, but at least as often I give you what the x and y values are. So just get used to that. All right, and I will then say etc. on this one. You should finish that out. Okay. And how am I doing for time? Not too bad at all. All right. The next thing I want to do is go on and look at the cycloid. That's problem 30. And I have not talked about the cycloid yet.
Yeah. What? I was going to ask that since whenever we got to.
Oh, okay. So you're going to ask me about problem 30. Very good. I want you to do at least one example in which we start with the geometry and figure out the parameterization of it. Sometimes we start with the algebra, like the x squared equals y cubed, and come up with the parameterization. But here we're starting with geometry. So this is a very ancient, well, you know, not ancient as in Greek and Roman, but ancient as in, 17th century. That's like 400 years ago now. So anyway, the cycloid, and you might have already studied the cycloid in calculus 2, but I think you can stand seeing it again, and I'm going to put more wrinkles on it than you probably got in calculus 2. But anyway, what happens? You've got a circle sitting on a straight line. What are we going to do with the circle?
Put a point.
Point on it somewhere. Well, how about right there?
And then roll it along.
And then roll it. Okay. So for the cycloid, we have this rolling sort of motion. Well, pretend that's a circle. And anyway, then this point, it moves up to about right there. Let's see if I can do better. That's a little better. So then this would go up to the top, maybe up there. And at some point, it might go all the way to the top. And our curve kind of looks like this. And then it starts the cycle over. And frequently we have that initial starting point at the origin. And we can consider this as having always been rolling. So from minus infinity all the way out there. And what I want to do is to figure out the arc length. Of course, the total arc length is infinity, but we've got a sort of a natural subdivision here. Let's take the arc length of one arch. And that's part A in this thing. You might say, well, oh look, that's a function of x. Y equals f of x. So I've got my y equals f of x equation where the root went right here. So I could calculate the arc length that way. But the problem is finding that function of x, y is a function of x here, is a real, well, it's tough. Let's put it that way. And so much so that writing y equals f of x, this is not an elementary function. And by that, I don't mean it's not so easy, although it's not so easy, but I mean it's technically it's not what's called an elementary function, and I think I've mentioned those before. Add, subtract, multiply, divide, power, root, exponential, logarithm, inverse, trig function, trig functions. It cannot be expressed as a combination of all of those, not as a finite combination. Maybe I could do a power series or something like that, but that's infinitely many operations. So anyway, here's one where it looks like you should be able to do a function, but you more or less have to set up a parameterization. So I could just quote the parameterization and get on with it. But I think this is such an instructive example that we'll just go ahead and work it out. So let me try to draw a pretty good circle here. Not bad. A little flat up there, but that's all right. Here's my track, my x-axis. I'm going to put the track on the x-axis. And let's say that it's already rolled a little bit away from the origin. And so, let's see, it rolls without slipping, which means the straight line distance is the same as the arc distance out to the point in question. Rolls without slipping, so the brakes are not on here. But, so, the curve's coming through here, and up through there somewhere. But I want to look at a point in the center. And let's say that I'm going to use a radius of A. Now, I don't like to use R for radius. I think I've mentioned that before, but R is used as a polar coordinate as a variable too much. The radius is going to be A. And the parameter I'm going to use is the angle between the where this point is and the vertical. And I don't like to use theta for this either. I don't like to use R for the radius, and I don't like to use theta for this angle, because theta, again, is too much associated with polar coordinates. Theta ought to be at the origin. But this is somewhere else, and so I'm going to call it theta. So I want to get x as a function of phi, and y is a function of phi. So here goes. First of all, the center of this circle, what are its coordinates?
The center of that circle.
One of them is easier than the other. Which coordinate is trivial?
It's A.
It's A. And A is the, which coordinate?
Y.
Y coordinate. So this distance is A. We got it. Now, for x, we have to worry a little bit. A, that's going to be a constant, but the x coordinate is varying. But now is where we do the rolling without slipping. Okay, so what is this arc length right here?
The distance it's rolled.
The change in x.
Well, the change in
It's
x
pi-
is
It's B, isn't it?
it's phi, not phi. If a was 1, it would be phi.
Okay, so it's A.
Phi, yeah, a times phi. B times a or a times b. That's my arc length. So again, in any circle, we have an S and some angle about a, well, no, don't use a for, well, how about R for radius? And theta. That kind of thing. So S equals R theta. That's what you learned early on. So I'm just applying the formula for the arc length of a portion of a circle. Of course, if theta is all the way around, if theta is 2 pi radians, then you have the arc length is 2 pi times r. So anyway, if it rolls without slipping, then this arc length is equal to this x coordinate right here. And so what I'm looking at is x and y. X and y are going to be the coordinates of the point I'm after. So this is not x. This is the x coordinates. Oh, it is the x coordinate center, so I'm going to write A, B here. But now I want to work my way from the center to the edge. And what I'm going to do is draw this perpendicular here. So that I've got a horizontal distance and a vertical distance. And I've got this slanted distance, which is that. So V is the vertical up to here. And my question is, well, if I know H and V, then what about X and Y? So, let's see, here's X and Y. And here is A phi comma A. And here is V and H. So what's X from this picture?
H?
Mm-hmm. I mean, what's X? No, it's not H.
Mm-hmm.
What is X? It's not H. This distance is X. This distance is Y.
You subtract?
You use
I subtract. Yeah. So I use the
A,
B5
A5,
minus H.
minus
and
A minus B.
A minus B. All right. And speaking of a whole bunch of letters, actually I don't do letters, I just do check marks. All right. And that distance is A. So what's H and V?
H is point sine a sine of 5 is equal to H, and then a cosine of 5 is equal to V.
And I too started out learning to call that symbol phi, but I prefer to call it phi. And I think that's what the Greeks would have called it. Any Greeks in here? We got all kinds. But anyway, how about this symbol? What's this called?
5.
Phi.
Or is it P?
It's phi. Actually phi, but then we'd never keep it straight if we have point P and then we have angle P, whatever. So anyway, so then this is A phi minus A sine phi, and this is A minus A cosine phi, and those are our parameterizations. All right. So we worked it out on the basis of geometry. And I wish I had time to do, like 8 more examples of this. I try to take a little bit of time on that in calculus too, but when we're at the end of the course, it's hard to take time to do anything. But this sort of thing, if you want to get the intuition, you need to look at more examples of this sort, and you can find them on the internet everywhere. But anyway, another good example, and I mentioned this in problem 31, there are variations on the cycloid, and the variation that you see most often is, which one is it? Is this the quartate? Yes, the quartate cycloid, where instead of going all the way out to the boundary here, you follow a point somewhere between the center and the boundary. And so